I'm Jeremy. I'm presenting for Vistek, and I'll give an introduction to timber diaphragms and how we approach them within our business. So first and foremost, what are diaphragms? So essentially, or fundamentally, diaphragms are simply horizontal elements that transfer the loads to the bracing elements. So these could be walls or roofs typically. They also form the function of tying the building together. So they do resist any horizontal loads that may be imposed from inclined columns or any out of balance load that the building may exhibit. In the context of the presentation, I'll really be talking more around floors and roofs. So when it comes to diaphragms, there's a number of different types or a number of different ways of delineating between different types of diaphragms, and the first one is flexible diaphragms. By definition, they act, as the name suggests, quite flexibly. They really act like simply supported members between bracing elements, and they distribute the loads to the bracing elements based on their tributary width or based on their load area. A diaphragm is actually considered flexible when the midpoint of the span deflects 2 times what you'd see in terms of lateral displacement. So that's saying that the floor is displacing as much as the walls are. When we're talking about flexible diaphragms, we're really talking mainly around stick frame, around floor trusses, I-joists, tech beams, those sort of things. They can be in cassette formation, they can be built in place, and they're usually held together with straps and quite light elements, things like that. When it comes to flexible diaphragms, and particularly in stick frame construction, the acoustic and fire detailing may require discontinuous floor plates. So it's, from an engineering perspective, it's really important to think about these things up front and try and get your head around how some of these detailing issues might impact your design. If there's discontinuities in the floor plate, maybe you need to consider about how those loads are going to get transferred across the floor plate, and particularly at the junctions at party walls and things like that. It's also really important to check the members and the sheathings for any actual loads, and if there are quite high loads inside the diaphragm, they may require additional struts and blocking just to transfer those loads to the bracing elements. So rigid diaphragms, so these are classified as having infinite stiffness. They do not deform, or they deform very little. And the load will be distributed to the bracing elements relative to the stiffness of the vertical bracing elements themselves. They are very dependent on span ratios and the distance between the bracing elements. So a very long spanning, say CLT floor, for example, can still behave relatively flexibly. And also, conversely, a CLT floor or something like that that spans very short distances between bracing elements can behave in a very rigid format. So most of my talk will probably revolve more around the mass timber side of the discussion. This is a 55 South Bank floor plate. So this here is supported on a series of CLT walls. So this behaves relatively rigidly, but really CLT itself is more likely to behave as a semi-rigid element, so somewhere between a flexible element and a rigid element. So diaphragm rigidity is really dependent on the number of or the frequency of bracing elements, such as walls or cave braces or frames or whatever you've got. So honeycomb structures, the diaphragm for those sort of structures will behave relatively rigidly. So what is CLT? So very quickly, CLT is a solid panel comprising of at least 3 layers of timber glued and laminated together. It has a primary and a secondary direction, so it has different in-plane stiffness in both axes as well. There is no design standard in Australia for CLT, so we really need to look at internationally what they do there and how they go about designing it. So yes, it has a primary direction, and so the predominant fibres, the outer fibres, are running in the primary direction, and the internal fibres are running in the secondary direction. So why is it different? Why do we need to think about timber differently? So first and foremost, timber is an orthotropic material, so it has different properties in 3 different axes. The bending thickness of the element doesn't match the overall member thickness, and it's a non-homogeneous or monolithic element. So if we're thinking from a CLT floor plate point of view, they're all tied together with screws and fixings, and these screws and fixings perform elastically, and the panels themselves, you can think of them being linked together with a bunch of springs, really. This makes the connection design and the detailing for these sort of elements really, really important. So within a diaphragm, you may also have things called collectors or drag strips. Now, these are elements that you may put in additional to your structure that are going to take the load back to your bracing elements, and they'll distribute them into your bracing elements. You'll also likely have cords or parts of the diaphragm that are going to resist the tension and compression of the in-plane loads. So these could be beams, they could be additional ties, they could really be anything that's going to resist the prying effect of the bending moment that's imposed on the floor plate. So CLT floor plates, they don't behave like a homogeneous rigid element. Now with current software, we have the ability to model floor diaphragms whenever we have a question about floor rigidity. It's pretty rare in a CLT design that the actual panel itself is actually going to govern the diaphragm design. And most of the strength or most of the displacement issues which are going to occur are going to come through your screw displacement, screw deformity, and just general joint slip. So why is this important? So screw stiffness really matters, and it makes a big difference on the actual overall performance of the floor plate. So this is actually a test that I witnessed a couple of years ago with SPACs, and we're just doing some very simple tests on screw deformation. And you can see on the right-hand side there the image of the screw. It's elongated and deformed quite a lot. So it's behaved in a very ductile fashion, and that's actually a very good sign for overall diaphragm performance. Conversely, fully threaded screws behave a little bit differently. They are more akin to brittle failure, so you need to be a little bit careful when using fully threaded screws, because you might be stepping away from the ductile performance of your diaphragm that you're actually really looking for. So how do we go about calculating screw stiffness? Well, there's a couple of methods we can use. The Eurocode has some guidelines on calculating the serviceability stiffness values, and also the ETA documents prepared by the manufacturers also have some guidelines on calculating screw stiffness. I'd just suggest you use these with a little bit of caution, because timber is such a natural material and it's subject to a whole bunch of variabilities. So don't necessarily take these values as gospel, and I'll go into that in a bit more detail later on. So when it comes to screw stiffness, particularly within floor joints and CLT panels, there's a number of ways you can connect them, but these are the 2 most common ways. And number 1 on the left-hand side is spline plates. So those are additional strips of timber that are laid inside a rebate and then screwed down into the CLT panels, and they tie the panels together. The other option, which is more common, is a lapped connection. Once again, with a lap joint and screws down through the joint. The 2 systems behave quite differently. So the one on the left, the spline connection, is quite a bit softer than what you get with a lap joint. So it's more likely to display more movement at these sort of connections. There is also the opportunity to put in fully threaded screws diagonally through joints and things like that. And as I said before earlier, just be mindful that if you're putting in fully threaded screws into these sort of connections, they do behave quite a bit differently. They're not the behaviour is not as ductile as what you get out of a partially threaded screw. So it's always wise to combine this sort of connection with partially threaded screws to give you that level of ductility. So some modelling strategies when it comes to diaphragm design. The very basic analogy is the truss analogy, which you can do with concrete floor plates and things like that. Your lateral resisting system, you generally nominate as some springs or the like. You designate some design strips You define where your chords are going to be, and then you sort of outline where your truss is going to be. You can then resolve your forces inside your truss members, and you can resolve those forces across the joint. A word of caution with these sort of systems is trying to calibrate your system so the truss that you're nominating somewhat reflects the stiffness that you're likely to see out of your CLT floor. That can be a little bit challenging, but I'm sure there's some methods that you guys can come up with to do that. Typically, I don't sort of do this sort of method, but it's widely accepted. Some other modelling strategies that are used as well is obviously the use of finite element. Just a word of caution with finite element is really understand what your software you're using, what its abilities are. Does it have the ability to model laminate structures like CLT and the like if you're doing that sort of floor system? Because it is different from assuming it's a solid piece of timber. So normally what you do is you can lump springs at nodes. You will get a concentration of stresses at these locations, so you need to resolve these and distribute them across the panel as appropriate. You can also obviously put in your beam, collectors, struts, walls, whatever you've got as your bracing elements, and apply stiffness to those elements or springs to those elements to get the load attracted to those areas. You can also distribute springs more frequently across the floor plate. This is obviously going to give you a better distribution of stresses and probably better performance and better integration. So that's probably taking it to the next level. So the example that I'll give is typically what we do in our office and how we approach CLT diaphragms. So in this example, this is one that Nathan's prepared for this presentation. We have a CLT floor plate. It comprises of just post and beam structure, some concrete cores, so fairly typical sort of structure that we would see. And for this example, I've only applied load in one direction. We would then break the floor plate up into, or panelize it into what we would need from a structural perspective, capturing our robustness strategy that we're going to deal with. So we'd apply our indicative panelization, and then we would also apply springs or line hinges to those elements and release them as appropriate. The spring stiffness we would get, we would calculate from the ETA or from the Eurocode. And then we would do our model. Now, models are quite sensitive, and they're only ever as good as the information you put into them. So we usually play around with the stiffness that we assign to those joints. So we would double the stiffness to get a higher load across the joints, and then we would likely halve the stiffness as well to see how, from a serviceability perspective, how it performs there, and then apply like a boundary method. And apply and work within that envelope and design appropriately. So this is a stress diagram of what we'd experience across the joints from a load perspective. And by playing around with those stiffnesses, by doubling and halving them, we can get an increase in joint forces of around 40%. So models can be quite sensitive in that regard.
Just hey Jeremy, it's Adam here, just in the background.
Yep.
There's a few people commenting about the audio, so if you can just speak up a little bit maybe, or
okay,
it's fine for 90%, it's fine for me, but I think some computers it's not coming through perfectly.
Okay, so. Is that better? Okay, cool. All right, well,
yeah,
I'll try my best. Cool.
Thanks,
so the other things that really influence your stiffness design and really can't be overlooked is the stiffness of the bracing elements. So a CLT wall panel, for example, is only going to be as stiff as the connections. So it's really critical to understand and get a good handle on how stiff those bracing elements are going to be. And also coupling walls or breaking walls, splitting walls and trying to rejoin them, they don't couple very well. So it's not like having a concrete element where you put a wet joint or something like that in it. The screws are still quite soft, so it's best to model those elements with a series of springs like I've diagrammatically shown there. The other things that influence your diaphragm design is actually the stability or the stiffness of your bracing elements. So if you've got hybrid elements with, say, a concrete core or something like that, that's going to be very strict, very stiff, that is going to attract a higher concentration of load. So those concentrated loads, you're probably most likely going to have to introduce things like drag strips to make sure that load can actually get into your bracing element. It's also good to have a handle on how stiff those connections are going to be and how they're going to perform. Some things to be mindful of. If you're looking at a diaphragm and you've got a very thin floor plate and you're looking at just a lapped connection, the way that a CLT panel is made by gluing the faces typically. It's not the edges. Not many manufacturers actually edge glue their panels. So to get load transfer across that joint, you're relying on a very thin throat of a fibre in the primary direction. And then the lower board potentially has a joint in it. So to get load transferred across that joint, you may need to consider ways to reinforce it, whether that's with additional screws, thickening it, or looking at maybe a spline plate or some sort of alternative connection. But then conversely, if it to have too many issues. So some things to consider when designing a diaphragm is the selection of the floor connection type does really influence the performance of the diaphragm. Most of the deflection that you'll see as a designer will be experienced through slippage of the fixings themselves and not so necessarily so much in the panels. The stiffness of the bracing elements, but particularly more so the connections of those bracing elements, really influences the distribution of forces throughout the entire structure. So yeah, really pay attention to how they are connected. And just because it's a solid wall panel, it's not necessarily going to behave like that. Bracing elements are only ever as good as their connections. I can't emphasize that enough. And really pay close attention to when you're using hybrid structures and making sure if you're using them as bracing elements and you've got a concentration loads, that your connection that you're applying reflects that. When we talk about modelling, just understand that all software has its limitations. There's never going to be one ideal model. The models are only ever as good as the assumptions that people use to create them. If you're doing a timber building, you're going to have to make a series of assumptions based on screw stiffness, material type, and things like that. And no model is ever actually going to be perfect. So it's probably prudent and quite wise to really consider using an upper and lower bound approach and play around with model sensitivity and get a good handle on what load you're actually potentially dealing with. And I also recommend really considering ways that you can actually simplify your model to really give you good confidence on how the model and how the system is actually going to perform, and if that's likely going to occur in your scenario. So when it comes to your final solution, really consider maybe design for manufacturing and assembly. Simplified assembly should always be a key consideration with any mass timber project. The last thing you really want to do is have 10 different types of floor connections across your project, because that's going to be no end of pain for the builder, but also as a checker going to check the installation can be a little bit troublesome as well. So there's software out there available. There's some free software which is Acrotim, which is sponsored by Wood Solutions. Doesn't do floor diaphragms, but it does bracing elements. So I'd recommend getting your hands on a copy of that. Wood Solutions support that, so speak to Adam if you've got any questions. And then also there's plenty of useful references online that are certainly worth reading. And I noticed that Daniel Marotta dialed in before, so there's one of Daniel's documents there that he prepared based on diaphragm design. So jump online and have a look at some of these documents. And then also the Wood Solutions design guides are certainly abundant and easily accessible. So by all means, download those. That concludes my presentation. It was very, very quick, but thanks once again. Thanks everybody for dialing in. Hopefully I haven't put too many people to sleep. So thanks very much.
Okay, so I'm Nathan, also an employee at Vistek, and I'll be discussing robustness. So essentially, just to give you some background, robustness comes about essentially from a risk assessment that considers structural element exposure and the vulnerability of those elements. So in regards to exposure, that's essentially the proximity to a potential accidental load case, and then vulnerability is sort of the inherent issues for a structural element, meaning that it might be more prone to damage. And then ultimately robustness is the resistance to the propagation of damage, and then the global survival of the structure due to those local damages. So as designers, we're really only concerned with the robustness part, and we're relying on essentially the codes and standards to have done the risk analysis to be prescriptive and therefore give guidance on the robustness requirements. Just to give you an example here, so if we take the case of a post and beam structure and we have, say, a loading bay, you're going to have a truck, so a heavy vehicle that's moving in and out, so that's the exposure. You might have columns nearby that could potentially be damaged by that vehicle should it you have impact loads, for example. The vulnerability in the case of, say, a steel column might be severe corrosion. With concrete, you might have excessive cracking or degradation, and for timber, you might have poor durability treatment and therefore rotting of the timber. So, and then just to give you some examples on disproportionate collapse and progressive collapse and the difference. Here you can see on the left an example of the Hyatt Regency Kansas City Hotel. So this essentially is the most or the biggest disaster in US history, essentially, for an accidental load case, or the deadliest, with I think 114 people were killed and over 200 more injured. So this was essentially 2 skywalks that collapsed due to poor connection detailing. So that was quite, clearly disproportionate to the local failure of that connection. And then, of course, it wouldn't be a robustness presentation without the Ronan Point example. So in the middle here, the photograph, everyone should be aware of this. Essentially a gas explosion that led to progressive collapse of successive floors. And then just that GIF showing a combination of the two. This came up on my LinkedIn feed over the weekend. I don't know if anyone else saw this, but quite scary, of course, for any structural engineer, but quite good timing too for this presentation. So fortunately, it's a good example of robustness and the redundancy and robustness that this structure has. So it looks like a cast in situ sort of moment frame construction, and you've got redundant load paths where the beams can act as cantilevers as well as the columns taking tensile loads. So just, scary stuff though. Okay, so some issues that can lead to robustness problems is the reliance on single members. So as you saw in the that Hyatt Hotel example, or in the case of transfer beams, for example, lack of redundancy, so no alternate load paths, long span beams and cantilevers. So these are prone to things like lateral torsional buckling. And so you might have it fully restrained generally, but if you had an event where you have a damaged floor that is, and the extent of which is not considered disproportional to the localized damage, this still may remove a significant amount relatively of that lateral restraint, which then could lead to failure due to lateral torsional buckling of these elements. And then flexible structures, so excessive or large deformations that might result in eccentric loading and P-delta effects. So general approaches are the enhancement of connections through things like horizontal and vertical ties, redundancy, so multiple load paths, continuous spans, for example, or two-way spans, catenary action. You need to be really careful here. Reiterating points Jeremy made, you need to ensure that your connectors are ductile and that they can accommodate the large deformations and rotations expected. Based on some of the research that's been done to date, you can see this photograph up here. This is a robustness assessment for a post and beam structure with column removal. And this showed that the large rotations and deformations at the connection points induce failure into the elements and the connections. And from what I've seen, lots of the sort of off-the-shelf connectors being used currently don't have adequate capacity to accommodate these rotations and deformations, and don't behave in a ductile manner. So therefore it's important to use different approaches such as key element design for this. Then you might look at notional element removal. So this is essentially assessing the structure and its performance to resist disproportionate or progressive collapse by removing individual structural elements one at a time. And this doesn't have to be purely quantitative. You could start with a qualitative approach and just by inspection make an assessment of the structure and look at if you were to remove certain elements, would that ensure that you've got a robust design? And then you might move into, if you believe that you can accommodate that and ensure that you've got a robust design, you might then move into some finite element analysis and things like that to do the final calculations. And then finally, if that's not going to work, that approach isn't adequate, you would need to implement a key element design approach. So this is essentially providing overstrength to structural elements to ensure that they don't fail, and therefore you don't have disproportionate or progressive collapse. Okay, so the codes in Australia are quite sort of limited. There's only sort of one page in the NCC on robustness, and there again in 1170.0, the section 6 provides some guidance on sort of ties and the capacities that they need to achieve and overall sort of stability of the structure. But it's not very prescriptive. It's quite ambiguous and hard to interpret. There's also the Structural Robustness Handbook, the ABCB one, but that really just references these codes, and it does actually though alert you to the sort of international design codes and everything that's out there. So that's one good part of that, but it really needs to be improved. It's not adequate at this stage. The Eurocode, that's a lot more prescriptive and comprehensive. It uses sort of consequence classes based on your building. And then this sort of robustness workflow here on the right, which is in the iStructE practical guide for structural robustness, that's really good. And I'd strongly recommend that people use this sort of approach or a similar matrix or something to work through and determine what the best approach to ensure that you've got a robust design. So whether or not you can simply use horizontal and vertical ties to achieve robustness, or notional element removal, or ultimately key element design. I mentioned the consequence classes. Generally in the Eurocode, I think it changes for certain national annexes, but generally speaking, it gives some sort of guidance on what disproportionate collapse is and limits the failure area or the extent of failure to the lesser of 100 square metres or 15% of the floor area. So if we take this example here on the right, that's a 9x6 post and beam grid. You could have localised failure of 2 bays across 2 adjacent floors, and that would be considered within the disproportionate collapse criteria. Then looking at key elements, so the recommended pressure to be used is 34 kPa or kilonewtons per square metre, and this actually comes from the Ronan Point gas explosion. So the post failure investigation determined that the equivalent static pressure would be 34 kPa. So that's why that example is used so commonly and so relevant for robustness, because it really influences the key element design in the Eurocode. Eurocode also gives guidance on impact loads, and it's also important to mentioned that you don't have to chase loads. So in the case where you're designing for, say, a minimum of 75 kilonewtons for a tie force, I don't know if people can see my mouse. I'm not sure. Oh yeah, I think you can. You don't have to chase those loads. So you've only got to design the tie and its end connection for that force. So let's say that you were designing a tie here for this beam to column. You don't have to then apply an external load of 75 kilonewtons to that column and then design the column accordingly. So you've only got to do it for the tie and its end connection. Oops, let's go back there. So an example for key element design, let's take if you've got a beam, applying the load laterally in the minor axis is quite simple. You just take the face area multiplied by that pressure and design it accordingly as a beam. So moment and shear in that direction, and do the same for the connections. In the major axis, however, you wouldn't apply that to your tributary width. You'll never get anything to work, or you'll pretty much just have a solid building resulting from it. You've got to remember this is a blast pressure, essentially. So you've got to be pragmatic about it and work through and determine an effective width that will remain from that pressure or any pressure up to that point. So essentially, you might find that a lower pressure means that a larger portion of the floor remains intact and the connections can handle that, which ultimately, so that pressure multiplied by the effective width could give an overall load that's higher than that of 34 kPa. I hope that makes sense. Let me know if it doesn't. Some other codes and design resources. You've got the UFC guide. That gives some comprehensive information, much the same as the General Service Administration guide. And then, of course, you've got the iStruct one, which I mentioned previously, that really outlines the Eurocode approach very well and gives very good commentary and explanation about all that. And then you've got the Wood Solution design guides, which are always very good. So in the case of element removal, if we take a column example, so here you would go through and work out how it's removed. You're going to have then excessive deformation within the of the columns and floor plate. You're then going to induce tensile loads, so it's going to have load reversal from compression to tension, as well as tensile, so catenary action in your floor plates and beam elements. And once again, I can't reiterate this enough, the importance of connection ductility, reiterating the points that Jeremy touched on. And here on the left, just an example of what you might see for a column tension tie, much, in a similar vein to what was used by Fast and Epp for the Brock Commons building. Then you might, if you believe that that approach might be suitable, you could go on to do a finite element analysis and actually assess the deformations and stresses within your structure to ensure that you can accommodate that. And even in this example, I found that that wouldn't work, so you'd have to design these as key elements. In the case of sort of load-bearing walls, so like a honeycomb structure, whether it be light timber frame or mass timber, it's much easier to satisfy the notional element removal requirements due to the fact that you can use things like rim beams to bridge or cantilever to pick up floor plates. Once again, you could use massive timber, so CLT or LVL walls to bridge those gaps as well. Or if you had sheathed light timber frame walls, you might be able to design those to act as deep beams as well. So floor diaphragms, it's all related. So with robustness, in the case of, say, floor joists or cassette floors with floor sheeting, you need to go through and ensure your connections can transfer the loads adequately that you're expecting. So if you're looking at catena reaction, I'll just point out, just general good practice is to glue and screw. I mean, it has other tangible benefits in terms of acoustics and vibration anyway, so I think that should always be used. But it just will enhance the redundancy and robustness performance. And once again, connection ductility really needs to be considered. As Jeremy showed, having sort of deformation and ductility such that you're going into plastic deformation of those ductile elements. So really what you need to do is look at a capacity design approach, much the same as you would for seismic design. So you're keeping your brittle elements, which in this case are your timber members, within the elastic range, while you're allowing the connectors to perform in a ductile manner and dissipate that energy. In a similar manner with, say, CLT lap joint, here again, as Jeremy mentioned, it'd be good to use a combination of fully threaded and partially threaded screws. You will need fully threaded screws to actually resist the high forces of the catena reaction, so the tensile forces, while you need some partially threaded screws to enhance the ductility performance. And some of the research that I've seen or heard at different seminars and conferences does show that a combination of these screws will enhance the ductility performance of these connections. So some key takeaways: robustness, crucial to safety and design, and it's very important of the design of any structure. So getting your head around these issues is really important. Prevention is always better than the cure. So if you can implement strategies to mitigate having to design for accidental load cases, let's take a case of an external column. You might put bollards around it to prevent impact loads or something like that. The Australian standards, in my opinion, absolutely must be updated and be more prescriptive. Until then, I'd highly recommend that you use Eurocodes or US standards to approach it. And for any building surveyors out there, much the same. I think you guys are probably as much at a loss and are confused as all of us engineers and everything as to the performance requirements for this. And that's where it's really not a level playing field at the moment, because it comes down to the individual's interpretation of the robustness requirements. When looking at the Australian standards, that is. Use a robustness flow chart or matrix similar to the one I presented from the iStruct-D guide earlier. And once again, connection ductility is crucial. So implementing capacity design approaches and ensuring that you have enough ductility in those connections to accommodate your rotation and deformation that you're expecting. That's really crucial. And to reiterate, the sensitivity analysis, so ensuring that you have upper bound and lower bound limits, that then you're getting results within that envelope that you're satisfied meet the requirements of robustness. And finally, Red Rooster, very underrated takeaway in my opinion. Rooster roll and chocolate mousse, you beauty. So very, very weird format here without being able to see anyone's reactions to that. Probably all, I hope you fell off your chair and didn't just cringe. But anyway, can see Adam's cringing, so I'll stop.
I thought it was very funny there, Nathan. I asked you if you can leave us with a joke or something because it lands very well on the webinar format. I thought.
Actually, I've got one more slide. I better just mention it. So at Vistek, we're currently rolling out some webinars pro bono for builders, architects, contractors, developers, etc. So if you're wanting to learn a bit more about mass timber, head to our website and you can register there. But yeah, so Jeremy's essentially leading that. I'll sit in on a few of them, but we're more than happy to do our best to give you or help share our experiences and help educate the industry on mass timber design. So thank you.
So I just realised I was mute. We've got a whole bunch of questions in the Q&A, so if everyone can just leave their questions over there, and we'll get through as many as we can right now. Jeremy, if you'd like to come back on with your unmute and your screen on, that'd be great as well. So I've got a few questions here, Nathan. We've got the first one, which I think we guessed was going to come up at some stage, but what finite element programs do you recommend for timber modelling and analysis?
Like Jeremy mentioned, it's more comes down to what suits you and your approaches, and it's more about the input rather than the actual software. I mean, any FEA software, for example, can be used to design these things. It's just going to mean, you know, how do you have to input the information in regards to the element stiffness and then essentially the spring stiffness between those elements. And you can do that in a variety of ways. We use multiple sort of software and certain ones that we think are more suitable. As Jeremy mentioned, the TimberTech one, that's quite good for certain design aspects. It, of course, has its limitations as to any other software. In regards to these sorts of things, yeah, wouldn't say that there's any one particular software that's best. So I certainly don't want to promote any software, I guess is the point. It's up to the individual to do their research and, you know, determine which software is the most suitable for their design situation.
Yeah, absolutely agree. I've got a good question here from Lisa Garner, who asks, should discontinuous floor plates be assumed as a default approach to, sorry, I just lost it, discontinuous floor systems for multi-res? So yeah, in the code it asks for discontinuous walls. What are your comments around that? So it's kind of where acoustics meets structural engineering.
Yeah,
this is always a problem.
I think the key to is to identify early on what it's going to be. If it's a significantly tall multi-residential building, then separation or discontinuity diaphragm might not be appropriate. It might be, from a structural perspective, it just might be really prohibitive. So there's other ways to deal with acoustic and fire rating issues. And if discontinuity is going to cause some issues, it's about identifying them early on rather than assuming that one thing's happening when the other thing might not be happening.
Yeah, and just further on that, I mean, there are resilient connectors. However, they might be cost prohibitive to implement those just to achieve, you know, the acoustic performance in the deemed to satisfy part of the code. Also, you know, locating things like your spline connections and things between discontinuous elements in certain areas. So you might actually locate those at doorways where you've already got an acoustic sort of issue or potential issue, certainly a weak point in the structure. Same with, say, bathrooms, making sure that the architecture has bathrooms backing onto each other. You might be able to put them there rather than from one living space or bedroom to another. So, you know, planning all of that out, I think, is important.
Yeah, absolutely. I might just add, a few weeks ago, we had a webinar from Amanda Robinson from Marshall Day Acoustics and Joel Parry-Jones from PKA, who touched on this exact topic. So, yeah, I think if you get a good acoustic consultant, then you can get the best of both worlds and get the continuous action of the floor plate, but also get the airborne and impact noise requirements solved.
Yeah, I've seen many solutions for acoustics with acoustic walls and suspended ceilings that mitigate impact, airborne and flanking issues. And, you know, they're being proven to work. So with testing, not just, you know, in a 2D analysis, theoretical analysis, that is.
So I might let Nathan and Jeremy, if you've got the questions up there, you can just scroll through and we can all just pick the ones you like.
Has anything been upvoted or whatever? How do we see any of that?
Not everything's been liked, but there's a lot of questions here. I've got a question here. What is the recommended ductility to be used in design of floor diaphragms and shear walls?
Sorry, I just saw Nick Hewson's question. I'll answer that in a sec. Sorry, what was the question?
So it's about the recommended ductility to be used in the design of floor diaphragms and shear walls.
So I guess,
yeah.
well, with sort of the approach for earthquake, I think that's where, once again, like I've seen it vary quite a lot, and it depends on how conservative you want to be. And I think that should come from the importance level. I think that'll change with more and more testing and research. I know there's a lot in that space with earthquake, and the performance, is phenomenal for these buildings due to lots of, ductile connectors. So I think you can, but I mean, I've used different ones. Like I've seen people use 3 and a combination of 3 and 0.67, and then others, right down the other end, 1 and 0.77. So I don't know. I think you need to look at the structure, and it's going to vary. There's no one answer that encompasses all structures. I mean, post and beam is going to be greatly different to wall and, a honeycomb structure where you've got far more connections. I think you need to be a bit more conservative for a post and beam where you've got crucial connections, whereas you've got a lot more redundancy in a honeycomb wall and floor construction.
Yeah, and I might just add for those listening on our Technical Design Guide 50, we've got recommendations for the ductility factors for the earthquake design, which I don't know off the top of my head, but I can share links with everybody who's listening to that design guide, so you can go out there and download it.
Just for Nick Hewson and the rest of the people, I actually decided to keep the Mo for today. I was going, do I shave it off? And I thought, nah, keep it on there. Just one of these ISO things that got to try something new.
So there's a few questions on generic timber design standards. For those who have gone from concrete background, there is a timber design standard in Australia, 1720 Part 1, and it includes all your light frame and your LVL and not explicitly, CLT. So a lot of your mid-rise building that can be covered by 1720 Part 1. When it comes to CLT, Nathan and Jeremy, you might like to add what standard you use based on what product you're using and where you're sourcing it from. So you, Jeremy?
Yeah, so if you're sourcing it locally, so we use a combination of, so if you're using local CLT, so there's a large CLT manufacturer in Australia, and if we're using their product, then we will use some partial factors from the Australian standards, as well as all the loading criteria from the Australian standards, and all the material factors for timber design, and appropriate it to that. If you actually speak to XLAM, they've actually got some technical notes on there that we've contributed to, and I'm sure Nick Hewson would be more than happy to share them around. If we're sourcing product from Europe and places like that, then we're most akin to using the Eurocode.
Is there any other questions in there, Nathan? We've got time for one or two more, depending on how big the question is, the scope of it.
I just saw, what was it? Yeah, I've lost it, but I will. The concrete topping. When you're using that for acoustics, can you consider that in the diaphragm design? It would depend on how you're actually connecting that. If you're not using shear connectors in the sense of screws to provide that shear flow transfer and getting some sort of composite action, I would suggest not, unless you can verify that you're going to have direct bearing. But if it's sort of on a membrane, that means that bond is lost, I wouldn't suggest that you use that to in combination with your structural assessment of the element.
There's a question here about preference for CLT joint half lap versus cross screws, and I presume it's talking about spline plates, things like that. The potential issue with a half lap, just with partially threaded screws vertically, is always your edge distance is always a concern, without having to make your lap excessively large. So in some instances, it might be required that you put a diagonal screw through the joint just to increase the strength of that joint. I did also show a slide earlier about half laps versus spline plate joints and the difference in softness between the two. So the two do perform quite differently. Spline joints are softer, so do behave a bit more flexibly than lap joints. So that's obviously going to be a consideration. But from a constructability point of view, it's actually always nice to have a lap joint, because from a seeker's point of view, you can put one panel down and drop the next one on top of it, and you don't get that differential deflection between the two. Whereas if you just butt panels straight up to get against each other, and if they're supported on different conditions, you potentially get some differential movement between the two panels, and you need to put the spline plate in to bring them back up to level. So that's my opinion on that.
Do we have time for one more quickly?
Yeah, if one quick one.
Someone just asked about how you design for the 34 kPa. So maybe I didn't quite make that clear for a beam. So essentially, it's just a pressure on the face of the element, or anything that's connected to that element that will still remain with that pressure. So maybe I'll use a different example. Let's say you had a column that then had walls butting into it, and let's say they were non-load bearing walls. So it's a post and beam structure, and you've got a party wall that's non-load bearing. You would probably find that most, if not all, of that wall will be blown out for that 34 kPa pressure. So then you would only apply the 34 kPa to the column area, so the face area. Let's say it's a 600 by 600 column. So one at a time in each direction, you would apply 34 kPa by 600 mil by the height of the column. But you might look at it and say, for 10 kPa, the entire wall remains intact. Now, if you've got column spacings of 6 meters, then you would apply 10 kPa to the tributary width and design the column for that, which will be higher than the 34 kPa on only the column area. Hope that sort of clears that up.
Yeah, makes sense. Oh, well done. Okay, thank you so much, Nathan and Jeremy, for your time today and helping us with this presentation. For everyone listening right now, if you could just feel free to, in chat, just show your appreciation, as we can't hear any applause, and Jeremy and Nathan might have a quick look before they go. So thank you very much.
Thanks, everyone.
Thanks for having us, guys.
Okay, just before everyone goes, just a quick plug again for the Wood Solutions Technical Design Guide. So we've got over 50 of them right now. Floor diaphragms and robustness have been covered in the past. And Technical Design Guide 50, which came up a few times already. This is really the Bible for structural engineers out there on how to design these buildings. So I will share a link to these guides after this presentation to everyone who's attended today. And just a reminder for everybody, next week we've got Peter Madison talking and doing a webinar on tiny homes. And I'll share a link to this also. So next Tuesday at 11 a.m. So thank you again, everyone, for joining us. I hope you really enjoyed that webinar, and I will see you next week.